Hello, my name is Philip Rissmann, and I want to show you how you can automate multi-scale modeling for magnetic materials with the help of AiiDA plugins. In material science, we're dealing with problems that cover several length scales. We typically start from the atomic or electronic length scale with the distances of atoms in a crystal structure, and then we have to go to much longer length and time scales where the microstructure of objects and then the macro scale of things that we can really touch in our everyday life become important. In magnetism, we also have this kind of problem where we have to cover these different length scales. On the one hand, we have the atomic scale of the atoms in our crystals. We have magnetic atoms that are magnetic atoms in crystal structures, so they live on a lattice. But on the other hand, we have the magnetic ordering domain walls that form, or solitons that can appear in magnetic textures. And these structures are typically much larger than the atomic scale. And so we have to bridge these very small length scales to these much larger length scales to be able to describe all this in a reasonable way. We can do this by starting from the atomic scale and do quantum mechanical simulations based on density functional theory. This covers then the angstrom or nanometer length scale, and it can be done, for instance, with the AiiDA-KKR code that we use in our work. We can then extract model parameters that map onto a Heisenberg model, and this is a classical model which allows to cover much larger unit cells and systems that contain millions of spins, and then study the dynamics of these spins and the emergent phenomena that appear here. For this, we will use the Spirit code that is also developed in Jülich. Both of these codes are connected with the AiiDA framework, which allows you to create workflows that combine these two steps and do the multi-scale modeling on the footing of AiiDA together with the complete provenance that AiiDA keeps during all these steps. And this then allows you to, starting from a quantum mechanical model, describe the emergent phenomena that appear in magnetic materials, get the ground state properties, get the dynamics of these magnetic textures, and also extract things like the critical temperature where magnetic ordering appears via Monte Carlo simulations. We can do this with the help of the extended Heisenberg Hamiltonian. The Heisenberg Hamiltonian is written down here, and it describes the interaction of all the spins. That the directions are given here by the vector n, and these spins feel an external magnetic field. They can have a single iron anisotropy. They interact with each other via exchange and Toloshinsky-Moria interactions, and also via dipole-dipole interactions. The model parameters which we need to feed in and which we need to get from our first principles calculations, we can extract with the AiiDA-KKR code, where we have to evaluate this formula here given on the right, where we just use the property that we have access to the green functions and exchange and calculate the exchange interactions for these materials. We can then do the next step and study the dynamics of these spins with the help of the Landau-Lifshitz-Gilbert equation that is given here. The LLG equation gives us the time evolution of the direction of all these classical spins, which we have now defined in our Heisenberg Hamiltonian. And all these spins, they feel an effective magnetic field. The effective magnetic field is the combination of external magnetic fields and the interaction with all its neighbors. And around this effective magnetic field, these spins will start to precess in a damped fashion, which can further be driven via spin-polarized currents and torques that exert some force on the direction of the spins. So let us take a look at a simple example for this. A simple example would be the ferromagnet of a BCC iron, and we start with our quantum mechanical DFT calculation, where we use the AiiDA-KKR plugin. So in the AiiDA-KKR plugin, we have defined several workflows, and we start with a self-consistency workflow where we just put in the iron structure and we tell the simulation software that we now want a magnetic calculation for this iron material. We can then go on and feed the output of this calculation to the JIJ workflow that also exists in AiiDA-KKR, and that allows us to extract these exchange interaction parameters. On the right-hand side here, you see the result of this calculation, where the exchange interactions are shown as a function of the distance between the two atoms I and J. And the positive sign here means they favor parallel alignment, and negative sign would mean anti-parallel alignment. So that is a little bit more complicated than just one number that we have to extract, but we really have to go to larger distances and take all this into account in our multi-scale model. In the second step, we can then go to the spin dynamics simulation software, and we use the AiiDA-Spirit interface for that. In there, we have defined the spirit calculation that takes the inputs which we have extracted in the previous step, and namely the exchange coupling parameters and the structure of where our atoms sit in the lattice. And we can then tell the spirit calculation that we now want to do an LLG spin dynamics calculation, and the simulation cell that we have created is shown here on the right, where we initialized all the spins with random orientations, so in a completely random state. We then go on and let the LLG dynamics evolve, so all the spins will start to precess around their local effective magnetic field. And if we wait for some time, all these spins will reach a steady state. And as you see here on the lower right hand side, the result is just a ferromagnetic ordering of all the spins in this simulation cell. So we have recovered the ferromagnetic ground state of iron and the ferromagnetic ordering of this simple ferromagnet. As you have seen here, the problem of magnetism covers multiple length scales, and this is very challenging if you just have a single tool at your disposal. So here you can use the combination of two tools, namely the AiiDA-KKR and the AiiDA-Spirit plugins, where you can find more information if you follow these GitHub links.